So we've seen the organization, anatomy, we've seen their function. Okay, let's add more details. Let's look at the receptors. Right now, we're still going, we're a little bit looking at them separately so that you have a clear picture of each one, and then we're going to try to integrate them right together. Yeah, that makes more sense. All right, let's see receptors. So I'm talking about the receptors worked on by the word postganglionic, right? Neurons. Yeah, the receptors you're going to find at the end organ, right? Yeah. So for the receptors, and of course, neurotransmitters and receptors. So we're looking at, let's look at the sympathetic postganglionic neurons, and then adrenal medulla location. Neurotransmitter for the postganglionic neuron is what? Is majorly norepinephrine, like you said. Actually, they don't make epinephrine, it's only norepinephrine for the postganglionic neurons. Yeah. Norepinephrine. Why don't they make epinephrine? And this is a broad question. Why do you think the postganglionic neurons cannot make epinephrine? Why are they making only norepinephrine? How do we make norepinephrine? Biochemistry. How do we make norepinephrine? So phenylalanine to what? Tyrosine, right? To dopa to dopamine, right? Dopamine to norepinephrine. Norepinephrine to what? Epinephrine. So the first enzyme in this pathway is what? Is phenylalanine hydroxylase, right? Phenylalanine hydroxylase enzyme. Tyrosine hydroxylase, second hydroxylase. Dopa decarboxylase. So this is decarboxylase. I think it should be dopamine hydroxylase as well. Hydroxylase. And then here we have a methyl, PNMT, I believe, which is a methyl transferase enzyme. So it's methylate. I'm going to add the methyl group, right, from SAM. SAM will donate methyl, CH3 to norepinephrine, so that I can form what? I can form epinephrine. Yeah, this pathway high yield. The cofactor for the first two enzymes would be BH4, right? BH4 by tetrahydrobiopterin. The cofactor for decarboxylase would be B6. Cofactor for hydroxylase would be vitamin C. And then PNMT is using what? Methyl, right? Donated by SAM, S-adenine methionine, right? Yeah. So these we should know. Why do postganglionic neurons, why can't they make epinephrine? Why do they make only norepinephrine? Because they don't have what? The last enzyme. That's why. They don't have the methyl transferase. That's why. So in the postganglionic neurons, they can only make norepinephrine. They can't make epinephrine because the last enzyme is not there. They don't have that. Adrenal medulla, however, has all the enzymes, including the last enzyme. That's why the adrenal medulla is the major source of epinephrine. But the postganglionic neurons only make norepinephrine. They don't make epinephrine. Yeah, because they are missing the last enzyme in the presynaptic, right, neuron. Yeah, in those neurotransmitters, in those neurons, don't have the last enzyme. So this is important. This last enzyme is also important because it's actually stimulated by what? Cortisol. So that is why it should be located right in the adrenal medulla, because cortisol comes from the adrenal cortex, right? So cortisol diffuses from the adrenal cortex to the blood flow, blood vessels, ends up in the adrenal medulla and stimulates this last enzyme, yeah, so that we can make epinephrine. Which means in patients with adrenal insufficiency, patients with cortisol deficiency, epinephrine will be low as well in those patients. No cortisol to stimulate the last enzyme, no epinephrine. The adrenal medulla will be making only norepinephrine. Or in tumors like pheochromocytoma, right, where we have too much methyltransferase enzyme. So a lot of tumor cells, there's a lot of enzyme. There isn't enough cortisol, physiologic cortisol, right, to stimulate all the enzymes. So pheochromocytoma actually makes more norepinephrine than epinephrine. Yeah, there isn't enough cortisol to stimulate all the methyltransferase enzyme. But in a healthy person, there's enough cortisol to stimulate most of the enzymes, and that's why the adrenal medulla makes what? 80% epinephrine, 20% norepinephrine. But in the post-ganglionic neurons, they make only norepinephrine because they don't have the last enzyme. Yeah. All right. So you can see so many things that can affect epinephrine or epinephrine production. Vitamin C deficiency might affect them. Hydroxylase is not working, hydroxylase. Patients with B6 deficiency, the carboxylase is not working, might also affect epinephrine levels, sympathetic nervous system. Yeah, that's why B6 have what? Peripheral neuropathy as a side effect, as a manifestation of its deficiency. Yeah, as well. Problem with the first step will lead to phenytonuria, right? Yeah. But then they can also have like those who can also have dopamine deficiency, dopa deficiency, but dopa 2 becomes melanin. And that's why patients with phenytonuria, right? They are pale because there's no dopa, there's no melanin, right? As well. Yeah. So I know that they can also dopamine also does a lot of other things, right? Which includes inhibiting prolactin release. So you may also see like hyperprolactinemia, right? This is why you might see high prolactin levels in patients with B6 deficiency, in patients with BH4 deficiency, patients with phenylalanine hydroxylase deficiency, right? They may have hyperprolactinemia because there's no dopamine. Yeah. So this pathway is super important to keep in mind. All right. So that's that. So going back here, sympathetic postganglionic neurons, neurotransmitter is norepinephrine, right? Where does it work? Norepinephrine works primarily on what? It can work on both alpha and beta receptor. It has higher affinity for alpha than beta, but it can stimulate both of them. Yeah. So it can stimulate alpha 1. We have alpha 1 receptor. We have alpha 2 receptor, which is GI. Alpha 1 is what? GQ, right? And then never can also stimulate beta receptor as well. Adrenal medulla makes mostly epinephrine, 80%, and also makes norepinephrine, 20%. So epinephrine can stimulate both alpha and beta, but it has higher affinity for beta receptors than alpha receptor. So it's going to stimulate mostly beta receptors, beta 1, beta 2, beta 3 receptors. And thankfully, all beta receptors are what? They are all GS receptors. GS receptors, all of them. They are all GS receptors. So basically, anywhere I expect, if we go back to our function, anywhere we expect the sympathetic nervous system to contract, lead to contraction of smooth muscles. Anywhere the sympathetic nervous system actually contracts smooth muscles, is likely doing that using what? Alpha 1 receptor. Because it is GQ. Right, remember GQ pathway? Okay, let's expatiate. GQ is what? If I stimulate GQ, what do? I convert what? PIP2, so activate phospholipase C, right? Molecular biology. You stimulate GQ, you activate phospholipase C enzyme. Phospholipase C enzyme will convert what? Convert PIP2 to what? To DAG and IP3, right? And then DAG stimulates what? Protein kinase C. IP3 opens calcium channels, so that will lead to what? Calcium release in the smooth muscles, so increase intracellular calcium in the muscles. And then calcium can actually activate PKC, but calcium will activate calcium, will bind to calmodulin and form calcium calmodulin complex. And then calcium calmodulin complex will activate what? Myosin light chain kinase. And myosin light chain kinase will phosphorylate myosin light chain, and that will lead to what? Smooth muscle contraction. Smooth muscle contraction. So anywhere sympathetic nervous system is contracting something, smooth muscles, uterus, right? Sphincters, contraction. The eye contracts the pupillary radial muscles, although it causes pupillary dilation because of the orientation of the muscles, but actually they are contracting their radial muscles in the pupils, they're contracting. Yeah. Right. It can also, there's also some alpha receptors on the salivary glands and co as well. Yeah. So can cause salivary gland contractions and release of saliva. So anywhere somebody is causing some sort of contraction of smooth muscles, receptor that will be on your mind will likely be alpha-1 receptor, because it uses what? GQ, which is where calcium comes in, causes smooth muscle, right? Contraction. That should be alpha-1. Okay, sympathetic. Nepinephrine. Alpha-2 is G inhibitory. GI, which is the opposite of GS, right? So we know GS is what? If I stimulate GS, I'm going to activate what? Activate adenylate cyclase. Adenylate cyclase will convert ATP to what? To cyclic AMP. Cyclic AMP will activate protein kinase A. And I know that this guy too can enter the nucleus. This guy there's a cyclic AMP response binding element, an answer site. Can stimulate the answer site and actually work on genes in the nucleus as well. Yeah, and then you're gonna see the effect, right, of that maybe hormone or like epinephrine or norepinephrine. Yeah, so that's GS. So alpha-2 is actually GI, right? Alpha-2 is GI. So alpha-2, so we know alpha-1 is smooth muscle contraction. Alpha-2 is centrally located. It regulates an autoreceptor. Alpha-2 is an autoreceptor. Let me show you what it does. So let's say this is our postganglionic, right? Sympathetic neuron. This is the end organ, maybe like the heart. So I have my beta receptors here. Beta 1 on the heart. This is the neuron. So I make norepinephrine here in vesicles. I stimulate the neuron. It releases norepinephrine, right, into the synapse, and the norepinephrine will bind to the beta-1 receptor on the heart, right, and stimulate them. Then say tachycardia and stuff. This is where alpha-1 is. Alpha-2 rather is going to be here. Alpha-2 is on the synaptic membrane. So the postganglionic neuron itself has what? Alpha-2 receptors. The postganglionic neurons, they have alpha-2 receptors on their membrane. So it's an autoregulatory receptor. It makes sure that what? So some of these norepinephrine you're going to release here, when you release them, they stimulate the receptor on the end organ, but then they're going to what? Also go and stimulate, right, the alpha-2 receptor. And since this is GI, they can shut down, inhibit, right, release of too much neurotransmitter. So it's a way of regulating the sympathetic nervous system. Alpha-2 is an autoreceptor on the postganglionic neurons themselves. And it regulates the release of what? Norepinephrine. That's what it does. So it inhibits the sympathetic nervous system so that we're not releasing too much norepinephrine and we don't have too much sympathetic response, right? So we call it a central, mostly central acting, right? regulatory receptor. And the overall function is what? It regulates the release of nerve. So it's kind of inhibitory. It inhibits the sympathetic nervous system. It's inhibitory. If you stimulate alpha-2, sympathetic nervous tone will go down. They're not going to release norepinephrine as much, or prevent too much release, right, of norepinephrine. So that's what alpha-2 does. Inhibits sympathetic nervous system. Epinephrine stimulates mostly beta receptors and then alpha as well. So everything epinephrine is doing to alpha 1 and 2, right? Epinephrine can also do that. Yeah. But it must primarily stimulate beta receptors. So beta 1 is where? Beta 1 is in the heart. That's why we have beta 1. Heart and kidneys, juxtaglomerular cells, right? Of the kidneys. So beta 1 increases heart rate, etc. And then what? Releases what? Renin. Stimulates the release of renin as well by the juxtaglomerular cells of the kidneys. Beta 2 is where? The lung. So mostly everywhere, let's keep it simple. Anywhere you will need, right? Smooth muscle dilation. Smooth muscle relaxation. Anywhere the sympathetic nervous system is relaxing smooth muscles. Bronchodilation in the lungs, yeah. Vessel dilation is going to be what? It's going to be beta 2. Beta 2. Why beta 3 is where? Is in the bladder. So to give you simple, beta 1, heart and kidneys. Beta 2, almost everywhere else except the bladder, where sympathetic is actually relaxing smooth muscles, is beta 2. So the lungs, bronchodilation, vessels, vasodilation, uterine relaxation, right? Beta 2. Then beta 3 will be the bladder relaxation. Beta 3. All right. So alpha 1, anywhere sympathetic is contracting smooth muscles, vessels, pupils, uterus, right? Alpha 2 is regulatory. It prevents the release of too much norepinephrine. So it actually suppresses the sympathetic nervous system. It's autoregulatory, mostly in the central nervous system. Beta 1, heart and kidneys, pressure control, things like that. Beta 2, everywhere except the bladder, I need to relax smooth muscles by sympathetic. Beta 2, lungs, lungs, uterus, vessels. And then beta 3, bladder, bladder relaxation. All beta are what? GS receptor. Alpha 2, GI, alpha 1, GQ. So once again. So parasympathetic. Now, for parasympathetic, postganglionic, right? Neurons are parasympathetic. What's the neurotransmitter? Acetylcholine, right? Is their neurotransmitter. But let me actually put something here. Let's put the exception to the rule for sympathetic postganglionic. So for sympathetic still, postganglionic, that uses acetylcholine will be what? The one to the sweat, which is which we use M3 receptor, which is also GQ, will be the one that supplies what? The sweat glands. Yeah. So that's sympathetic cholinergic, right? Postganglionic. Right. So what we can see most of them, so for the postganglionic, most of them are norepinephrine. Adrenal medulla makes epinephrine and some norepinephrine, but then postganglionic will be right. Yeah. The cholinergic rather, postganglionic sympathetic will be to the sweat glands only. But for the parasympathetic nervous system, all the postganglionic here use what? Acetylcholine as the neurotransmitter. Yeah, cholinergic pathway acetylcholine. And the receptors will all be what? Muscarinic receptors. M1, M2, M3. Those are the major ones. There's also M4 and M5, but know these three. These are you, and they are also two of them GQ, M1 and M2 GQ. M1 and M3 rather GQ. M2 is what? GI. Right. So M2 and alpha 2, right? They're the same. GI. The twos. Alpha 2, M2, they're inhibitory. Beta 2 is GS, all the betas GS, right? Alpha 2, M2, GI. All the betas GS. All the ones besides beta, GQ. Can you see the pattern? So alpha 1, M1, GQ. Right. All the twos except beta, GI. Right? Then 3, M3, GQ. Right? Beta 3, definitely all the betas GS. So once you remember that, any beta you see is definitely GS. No, so that is straightforward. Done. Outside beta receptors, all the ones are Qs, GQs. So M1, alpha 1, GQ. All the twos outside beta, M alpha 2, M2, GI, inhibitory, right? And then we now also have like any other receptor you can think of besides the ones and the twos, which includes which will be M3 now, will also be GQ, just like M1. Yeah. So that is the pattern. All the betas, GS. That makes it easy to remember. I don't have to memorize that one. They're the same. All GS, stimulatory, destimulatory. Now, when you leave beta receptors out of the picture, you're left with alpha receptors and M receptors. M will be parasympathetic, except sympathetic cholinergic, right, to the sweat glands, which is also M. And then we have the alpha receptors, which are also sympathetic. All ones, they are Qs, GQs. All twos, they are inhibitors, GI. Then any other receptor outside that will also be Q, right? GQ. Okay, so where's M1? M1 is usually in the central nervous system, right? So head to toe, M1 central nervous system, M2 heart, M3 everywhere else. You can see, simple. M1 central nervous system, M2 the heart, M3 everywhere. And let me put this as nervous system, not just central, because you can also find M1 in like the enteric nervous system as well, right? Yeah. So let's say nervous system. That's where M1 will be. So nervous system, central nervous system, as well as what's the name? Enteric nervous system. Yeah. Central enteric nervous system. So central brain, spinal cord, enteric nervous system. The nervous system that controls the GIT. Yeah, they have a lot of M1 receptors there. Then M2 will be the heart, and then M3 will be everywhere else. Give me a moment, okay? All right. So M1, central enteric, M2 heart, right? And then anywhere else there's parasympathetic nervous system working or stimulating besides the heart, besides the central and enteric, right? You're thinking likely M3. Yeah, receptor. So it makes it easier to kind of remember which is which. Yeah. All right. A lot of information already, right? So quick recap. We started from here, organization. We know, right, where the overall organization, preganglionic, postganglionic neurons, right? Yeah. Where do preganglionic neurons come from for sympathetic? We know where they're coming from. And then we know the major ganglia they're going to interact with. And then you know where those ganglia will project to. Yeah. It kind of makes sense based on their location and all that. Yes. Know the neurotransmitter for each, for the pre, as well as the post ganglionic. And then the neurotransmitter will also give me an idea of which receptors will be on the target, right, of those ganglia, of those neurons. Yeah, the sympathetic and para. There's some parallel between them. The parallel is that what they both have pre and post. Yeah, and then there's differences. Another parallel is that the pre use the same neurotransmitter as well as the same receptor in both sympathetic and para. Most of the post in sympathetic, they are adrenergic, except sweat glands, right? Yeah. While for parasympathetic, they are all cholinergic and they use muscarinic receptors. Yeah. Another difference would be the pre in sympathetic, right? They are shorter. The distance they travel, right, is shorter compared to the para, which means the ganglia in parasympathetic nervous system, right, they are closer to the end organ. The ganglia in para are closer to the end organ. So the pre in parasympathetic, they are very, very long. They travel a longer distance, while the post are shorter, travel a shorter distance. But in sympathetic, the pre travel a short distance, while the post travel a longer, right, distance, or they travel like equidistant, maybe. Yeah. So that's another different structure, anatomically speaking, organization speaking. Then now that we know the organization, where they come from, things like that, we talked about overview of how and where they work. Yeah, skin, eye, etc. Oh, let me add one more thing here to this function. Blood vessels, right? Blood vessels. So blood vessels, peripheral vessels. Blood vessels, sympathetic definitely constrict, right? Blood vessels. So alpha 1 constrict blood vessels. And then sympathetic can also dilate vessels, right? Using the word beta 2, dilate vessels. And then on the other hand, for the parasympathetic, right? There's M3 receptor, right? In the parasympathetic nervous system. From the para receptor on blood vessels is actually M3. Now, this receptor is what is on the endothelial cells. It's not actually on the muscles themselves, unlike alpha 1 and beta 2, right, that are on the muscles. M3 is on endothelial cells. And what it does is that when you stimulate M3, it releases what? It releases nitric oxide, right? It releases nitric oxide, and then this will dilate. Yeah, to relax the smooth muscles, right? And can dilate the vessels. So blood vessels, we have alpha 1 constrict, sympathetic. Beta 2 can dilate vessels, which is also sympathetic. Yeah, but the predominant tone at rest is alpha 1. Yeah, right. Then M3, which is a para receptor, is actually on the endothelial cells, not on the muscles themselves. Muscles, it can release, once it's stimulated, the endothelial cells release nitric oxide, and then nitric oxide will do what? Dilate or relax the smooth muscles, and that leads to dilation, right, of the blood vessel. Yeah, important. Good. So this is overview of their function, and then we kind of try to put the receptor there as well. What they do, receptors are, and then we will try to kind of summarize the receptors individually, what the receptors are. So what's the structures, the transmitter, and which receptors they work on, and what receptors do. And then know the molecular basis, right? How the receptors work, the signaling pathway, right? For the receptors to be super high. So that is, yeah, organization and function. of the autonomic nervous system. Let me add one more point here before we move to the pharmacology part. You see, not all receptors, right, in the autonomic nervous system are directly innervated. Not all receptors are directly innervated. You see, beta-2 receptor. Beta-2 receptor is not directly innervated, doesn't have a post-ganglionic neuron, right, innervating it. Yeah, it doesn't. So which means basically norepinephrine released by the postganglionic neurons can stimulate alpha-1, alpha-2, and beta-1 because those are neurons that will go straight to the nerve and form like a synapse, right? Directly stimulated. So the postganglionic neurons that release norepinephrine, they directly innervate what alpha-1 receptors, beta-1 receptor, maybe even beta-3 receptor. But you see, beta-2 is not directly innervated. So it is only stimulated by what? By epinephrine circulating in the blood. Beta-2 can only be stimulated by what? Epinephrine circulating in the blood by the adrenal medulla. It is not directly innervated. So it's not controlled by norepinephrine at all. It's only epinephrine that can stimulate beta-2. Yeah. Or maybe circulating epinephrine as well. Yes, circulating can do that, but not innervation, not the postganglionic neurons. So it's not innervated. M3 receptor is mostly innervated, right? Except the M3 receptor on the blood vessel. Yeah, so the M3 receptor, it is mostly innervated, but there's an exception to the rule. The M3 receptor on the blood vessel is not innervated. M3 on blood vessels, the endothelial cells of blood vessels is not innervated either. Doesn't have direct innervation. It is also stimulated by what? By circulating acetylcholine. It's stimulated by circulating acetylcholine, right? Not by the postganglionic neuron. Those are the two exceptions that we must know, and it's important to know that. I'm going to tell you why it's important. Yeah. So all these receptors, most of them are directly innervated by some postganglionic neuron, except what? Beta-2 receptor, which means it's stimulated by what? By circulating catecholamines, epinephrine or epinephrine released by the adrenal medulla, and M3 receptor on the endothelial cells of the blood vessels. Also, it is not directly innervated, which makes sense. It is facing the blood. It's on the endothelial cells, right? So it's facing the blood. There's no way nerves will enter the lumen of the vessels and then get to it, right, per se. So it depends on circulating acetylcholine in the blood to get stimulated, which is a vasodilator as well, M3, right, on the endothelial cells. So those are not directly innervated, which means if I give you a question, experimental question, a patient underwent we did an experiment, right? Bunch of animals, experimental animals in the lab. We removed their what? Adrenal medulla, right? There's no medulla. We removed the adrenal medulla or blocked it somehow, which means the adrenal medulla is not releasing, right? Catecholamines into the blood. The examiner will ask you which of the following sympathetic function will be affected. Which sympathetic function will be affected if the adrenal medulla is not working or has been removed or blocked or something? Then your mind will be, okay, the only receptor that depends exclusively on the adrenal medulla, right, is what? Beta-2 receptor. It's not directly innervated. All the other receptors will still be working because they have innervation. Norepinephrine will stimulate them from the postganglionic neurons, but beta-2 will not work, which means that what? Patient cannot dilate their airway. Where's beta-2? The lungs. Bronchodilation will be limited, will be affected. Where's beta-2? Uterus. Uterine relaxation will be limited.